chapter 19 on electric potential. We're going to talk about electric potential, which is a lot like gravitational potential. Gravitational potential energy applies to the energy an object has because of its mass when it is in the presence of a gravitational field. Electric potential refers to the energy an object has because of its charge when it is in an electric field. So we had to look at electric field before we could look at electric potential. So let's start taking a look at electric potential. So here we have a charge Q that's in an electric field, right? And so it can do work. Just like a mass rolling downhill can do work, it can do work. Now, as it does work, as it goes through the electric field, it loses energy, just like a mass going downhill loses energy. So the work done by the charge as it moves along is the opposite of the change in potential energy, electrical potential energy. So we define, just like we did for the force, we define the electric field as the force per unit charge. We're going to find the voltage as a potential energy per unit charge. That way you have a potential energy or electrical potential that's independent of any particular charge that we're going to end up putting in it. All right, so, and in particular, we don't think about it this way too often, but when we talk about change in potential energy due to your position in a gravitational field, we talk about you go from one height to another. Well, here we're going to talk about going from one point to another, VB to VA, right, is the delta V. So delta V is the voltage or electric potential at point B minus the electric potential at point A. All right, so delta V, VB minus VA is delta P over Q, change of potential energy per unit charge. So if this is what voltage is, then 1 volt, or the symbol, the unit for voltage, must be a joule per coulomb, because we have joules in the top here, we have coulombs in the bottom, so 1 volt is a joule per coulomb. In terms of doing work, when we talk about electrical potential and doing work, right, what does that really mean, right? Well, let's take a 30-watt lamp. 30-watt lamp. You're familiar with lamps. You're familiar with light bulbs. They typically range compact fluorescent, sorry, typically 6 watts. An incandescent lamp, 30 watts, 45 watts. So watts are joules per second. So we've got a 30-watt lamp, or 30 joules per second, hooked up to a 12-volt battery. And now 12 volts is 12 joules per coulomb. So in 1 second, right, in 1 second at 30 joules per second, the potential energy changes by minus 30 joules. And we have a voltage change of 12 volts. So if we take this delta V equals delta P over Q and solve it for Q, we get Q, which is the change in potential energy of minus 30 joules divided by delta V, which is 12 joules per coulomb. We get this is 2.5 coulombs, or minus 2.5 coulombs is the amount of a charge that moves, the number of electrons, or the total charge of the electrons. And if we then say, well, we know one electron is 1.6 times 10 to the minus 19 coulombs, we end up with this, during this 1 second, 1.56 times 10 to the 19th electrons moved. Right? A lot of electrons. A lot of electrons. Well, we move electrons around all the time. All right, so now let's suppose we do something different. We take an electron, we put it in a electric field, and we accelerate it through a potential, so that instead this time we're talking about, okay, the potential we're going to give it through, send it through, is equal to QV. Well, that potential gets converted over into kinetic energy, right? So the kinetic energy of the electron changes by also QV. We've got conservation of energy here. We lost this much potential. We gained this much kinetic. All right. And This adds, if we do this through 1 volt, right, we say it adds 1 electron volt of energy to the electron. 1 electron volt is just 1.6 times 10 to the minus 19 joules. You're like, well, why do we make up this crazy unit, the electron volt? Well, the reason we make up this crazy unit is whenever we talk later in the semester, when we talk about atoms and atomic spectra, and we talk about individual photons, the electron volt is a very handy unit of measure for atoms and molecules and fundamental particles like electrons, and for very small particles like protons and neutrons. It's a very useful unit for those types of situations. Right now at CERN, they're working on getting up to 14 tera electron volts, 14 times 10 to the 12th electron volts at the accelerator there. Um, Sounds like a really high energy, right? But when you look at it in terms of joules, well, it's not really all that much, right? All right. Because of energy conservation, said before, the change in potential energy ends up being QV, which ends up being the change in kinetic energy, which ends up being 1/2 mv squared, the kinetic energy. All right. So if we know we accelerate an electron through a voltage V, we can find, using 1/2 mv squared equals QV, we can find the velocity it ends up at, right? So let's take velocity, let's say 100 volts. We got 100 volts here. We have Q is minus 1.6 times 10 to the minus 19 coulombs, right? The mass of the electron is 9.11 times 10 to the minus 31, and that all needs to be inside the square root there. Now we calculate this and we get a velocity, right, of 5.93 times 10 to the 6 meters per second is the velocity we end up with. And this is approximately 2.13 times 10 to the 7th kilometers per hour. But note, the speed of light is 3 times 10 to the 8th meters per second. So we're up 100 volts, accelerates an electron to about 2% the speed of light, right? 2% the speed of light. Not bad, right? 100 volts gets an electron up to about 2% the speed of light. Now, part of this is that electrons are just so light, right? 9 times 10 to the minus 31 kilograms. That's a big part of it. Electrons have very little mass. All right, if we now look at a uniform electric field, right? Uniform electric field, then V from A to B is just the distance D times the electric field, right? We got distance we go through D, we've got an electric field, VAB, V from A to B is just D times E. That's the work done per unit charge. This is the energy per unit charge, right? Distance times force divided by charge. Remember, electric field is force divided by charge. So this is for the work done per unit charge. This is the potential energy per unit charge, all right? And we can solve this for the electric field, and we get electric field is the voltage divided by the distance. So we have a new set of units we can use for electric field. We started off with electric fields or newtons per coulomb, but we can also talk about it in terms of volts per meter, or the change in potential energy per meter, right? Change in potential energy per meter. Here we have the force per unit charge. All right. Important things, important E fields that you need to kind of have in the back of your mind if you ever do any high power work. Once you get up to 3.6 times 10 to 6 volts per meter, the air breaks down. Basically, what happens at this point is that the electric field is so strong it starts pulling the electrons one way, starts pulling the protons the other way, and it ionizes the air. And you end up with something we call lightning, or electric sparks, or things like that, right? So this is the point at which air breaks down and electrons and ionized molecules start flying all over the place. If we look at this as parallel plates like we've got over here, right? We just ask the question, what voltage can we put on these before it breaks down, right? Well, we want V, the voltage from A to B equals dE. We know the distance. We know the maximum voltage we can put on. And when we look at that, we find out we can put up to 75 kilovolts, 75,000 volts on these plates if they're 2.5 centimeters apart. All right, so if we journalize this a bit, electric field is minus the change of potential over the distance you move through. Delta S is just the distance from A to B. The minus sign just means the electric field points in the direction of decreasing potential, right? Electric field points in the direction of decreasing potential. As a positive charge goes through the electric field, it is losing energy. It is losing potential energy. Work is being done with it, right? All right, that's it for this segment.